So what we're going to be talking about here is a mixture of two things. The first of which is going to be just understanding equations and the language that's used for it. So if you look on page 4, we have on here some reactions. We have calcium carbide and water. We have acetylene and oxygen for reaction 2. And what our goal with this is to look up at page 4, and I love how I'm making marks and I'm not meaning to, but you're meant to look at page 4 and use that for what we see on page 3, and so, or on page 5, sorry. And so if we look at this, we can just look at a few things. What elements are in the compound calcium carbide? And so if we look at calcium carbide up here, we can see, oh man, here we go. We can see that we're getting both calcium and carbon, and so we would go ahead and write in calcium and carbon. All right, and so we're using this information to help us out. A few things that we can highlight, a few terms we can highlight as we're looking at this. The first of which we have products, right? So products, we have reactants, we have subscripts, we have coefficients, we have molecules, compounds, and elements. All right, so those are different things that we need to take into account. And so if we look up, we can walk through each of those, and the way that we can go ahead and walk through each of those is by understanding again that we're looking at reaction 1 and 2 on page 4. So we can look at question number 2 on page 5 that is marked down here. Go make sure we're on this. So what are the products in reaction 1? Our products are going to be what's produced. So we have this arrow. This arrow is showing that there's a chemical reaction happening. So in showing that arrow, anything that's a product is going to be found on this side. We can remember that because of the fact that products are produced, and so anything that's on the right side of that arrow, which will change later on as we go. We're not just going to have a single arrow, and we'll get to that later on. But we're going to have our products on the right side, and therefore our reactants, as it's another term we have to know, our reactants are going to be on our left. And so, in other words, we get what reacts turning into what is produced. So what are the products in reaction 1? Well, we look at reaction 1 and we see that calcium hydroxide and acetylene are the two products that we see up here in reaction 1. So we can even go through and label that as our products. What are the reactants in reaction 2? Well, we look at reaction 2 as acetylene and oxygen, and well, if that's what's reacting, if that's what's on the left side of the arrow, that's what we can go ahead and write in for our answer. So we have our acetylene, and we have that reacting with oxygen, therefore those are the reactants. So we have our elements inside of a compound, which real quick we can go ahead and write down. The main difference between these, when we're talking about molecules, more often than not, what we're talking about are covalently bonded. Our compounds are going to be ionic more often than not. And then when we're talking about elements, anytime we see a single element, we'll put the number there. So one single element, we're going to be dealing with elements. So when it asks us what elements are in the compound of calcium carbide, we know it's a compound because calcium and carbon are metal, non-metal. So the relationship that we see there is going to be one of an ionic relationship. All right, list the subscripts in reaction 1. If we break down that word subscript, we're saying that it's written below. And so any of those subscripts are going to be written below those those numbers. So in calcium carbide, we have CaC2, we have H2O in water, we have in calcium hydroxide CaOH2, and then in acetylene we have the numbers 2. So really we have 5 2s in that first reaction. And so if we're listing those subscripts, we see that subscript 5 different times, again up here written below in each of those molecules / compounds / elements that we're dealing with. The last thing we'll talk about here is the coefficients, and the coefficients, again, this one's talking about reaction 2, but the coefficients are the things that are written in front of the molecules, elements, compounds, and what these coefficients do. So for acetylene and oxygen, we have the numbers 2 and 5. So real quick, if we answer this, list the coefficients in reaction 2. Well, we have a coefficient of 2 in front of acetylene. We have a coefficient of 5 in front of oxygen. We have a coefficient of 4 in front of carbon dioxide and 2 for water. And really what these are telling us, if we look at the model that's given to us in this, if you see the fact that we have, again, those 2 acetylenes, we have 1, 2 acetylene molecules. All right, so that number, that coefficient, for what we're dealing with right now, we'll get into kind of defining this later. But that's telling us how many molecules we're dealing with. Again, we have oxygen. There's 5 oxygens, 1, 2, 3, 4, 5. And so we're really just counting over and over again how many of those there are. We'll talk more about why it's important to have, for example, 2 acetylenes and 5 oxygens, and we'll get into that more with stoichiometry. But what we need to understand is that we need 5 oxygens, right? 5 O2s, again looking there, 5 O2s that will react with 2 acetylenes in order to get all of these products, right? It's important to understand that as we're dealing with this, as we're talking about reactions, there's this idea of conservation of matter, and we cannot create or destroy matter, so we can't just all of a sudden gain an extra oxygen. We can't all of a sudden delete or destroy a carbon, whatever the case may be. But as we're looking through this, we have to use the different building blocks, the Legos, if you will, of acetylene and oxygen. We'll rearrange that. We'll see some bonds broken. We'll see some bonds formed despite being ionic or covalent, and we'll see new bonds form, creating these new products. So that's really what it is that we're seeing. That's what we need to take out of this whole idea of this introduction to equations and the general language. So feel free to get the rest of this page 5 done. It's good going into this language. It's good practice. It's good understanding what's going on, and some of the concepts we even talked about in the last 5 minutes or so is going to be asked between questions number 6 and 15. So it'd be good for you to do that. So make sure that you do. Same thing with page 6. It's just looking at more practice with understanding the language of chemistry. And so knowing coefficients, knowing what compounds are, knowing what elements are, reactants and products and molecules and atoms / elements. Knowing those is important for what we're doing. But we're going to forego that for this video, and we're actually going to skip ahead, and we'll kind of stop here halfway between page 7 and 8. And the main goal with this is to take what we see on page 8, which is where it says balancing equations, number 1, and making sure that we understand how to model this idea of conservation of matter. And so you may have done at some point in time in your science tenure this idea of balancing equations. And so we'll go through a few examples of this. I'll throw 5 up here as well. We'll go through this, and then that way if you have questions you can ask, but you can kind of look back at this as many times as you want. So we get some zinc oxide with some hydrochloric acid. Gives us zinc chloride. right? Remember that as we're writing these, we're gonna get to a point where we're balancing equations, but making sure that you remember that when we're writing ionic formulas like zinc chloride, we're balancing those charges. Zinc has a +2, chlorine is a -1, and that's why we're seeing that. So if we look at this and we decide to balance this, I'll change up the color so hopefully it's a little bit easier. But again, our goal is to model, it's to show that whatever we start with, we end with. Again, we're not creating, we're not destroying matter, but we're seeing that it's conserved. And so over on the reactant side, again, going back to that language of chem, on the reactant side right now, we have 8 sulfurs and we have 2 oxygens. And that's, again, just telling us how many we have on that side. The product side, we have one sulfur, and 3 oxygens. And so again, this is showing us that there's a problem here, that if we were to leave it like this, we're seeing 7 sulfurs disappear, and we're seeing 1 oxygen come out of thin air, and it just does not work like that. So the way that we can look at this, and the way that I do this, and by no means do you have to do this each time, but it's beneficial, it's helpful as we get started. But we can see how many of each atom, how many of each element we're starting with on each side, and that can give us a good idea as to where to get started. A few pointers with this is we want to do oxygen and hydrogen last. Oxygen and hydrogen will balance last. More often than not, we're just seeing a lot of oxygens and a lot of hydrogens in many different spots. So if we could save those till last, that'll be helpful. And I will go backwards actually. Another rule that we can stand by is anytime we see an odd number, we want to make sure that it goes to even. And that'll just help us out, and we'll kind of see how that goes. And so at this point in time, when the formulas are written for us, the only thing that we can change are these coefficients. So you can't go back and rewrite and put in some random subscript. Reason being is because, again, the bonding, what we've done with bonding, ionic, we're dealing with the charge, and covalent, we're dealing with what allows for that full outer shell, that full valence shell. So we cannot change subscripts, so we have to be sticking with coefficients. And so we can go here, we can add, how we can do this is we can add an 8 to this. The reason we do that, again, is to balance out our sulfurs. So what I'm going to do is I'm just going to scribble out this 1. And so since we have a 1 times this invisible 1 times 8, we get 8. We see that the sulfurs at this point in time are conserved. They're balanced on the reactant and the product side. But that doesn't just change how many sulfurs we have, because that 8 is distributed to the oxygen. And so so what we have now is a new amount, which is 24, because 8 times 3 is 24. And so we have this new value. Our sulfurs are balanced. Now all that we're left with is our oxygens. And so if we need 22 more, what we're going to do, again, in order to change that value of 2 on the reactant side, is we're just going to put a coefficient of 12 there. And what that does for us is it allows us to see that our equation is balanced. So if I were to ask you what are the coefficients for this, you just change which page I'm on, which doesn't help. If you go through and look at this, our coefficients would be 1, 12, and 8, just as an easy way to communicate that. So we have that. We'll go through one more example, and then you can get some practice in on your own. But again, we're going to do the same thing where we're labeling which elements we have here. So we have zinc, we have oxygen, we have chlorine, and we have hydrogen. And if we remember from what we just said, we're going to make sure that our oxygen and hydrogens are done last. Again, just to make life easy. It's just a good habit to get into. If you want to try going for it first, by all means, and you should get the same answer. But on this reactant side, we're getting all a value of 1. We have 1 of each of those. We have 1 zinc, 1 oxygen, and then 2 of our others in there. So again, if you want to be bold, you could start with hydrogen, but I'm going to start with chlorine again, just to get in good habit. And so if we look, in order to balance this, we can put a nice little 2 in front of that hydrochloric acid. That changes our chlorine value to 2, and actually it solves our problem by doing that. So now we are balanced. Some equations are easy, like this one. Some equations are more difficult, and we'll get through all of those. But again, the main idea with this, what we're trying to understand through all of this, is that the reason we balance is in order to model conservation of matter. And if we look at what conservation of matter is, again, this is looking at the fact that matter cannot be created or destroyed. And when we do that, when we balance these equations, when we put these coefficients in, I keep doing that. When we put in these coefficients, it allows us to, cannot be, multitasking is hard, created or destroyed. All right, when we put these coefficients in, it allows us to see what's going on at the molecular level, like we did here, where we're seeing how many of these molecules, how many of these compounds are needed to react with each other.